Good afternoon, class. We are looking at Chapter 5, Integrals. We're going to cover 5.1 to 5.3, the fundamental theorem of calculus. Five point one through 5.3, the fundamental theorem of calculus, also known as FTC, and 5.4, the substitution rule. So to remind you what we did, a quick recap. The derivative of kx is k, therefore the integral of k dx must be kx plus c. The derivative of x to the power of n, we are using the power rule, is nx to the power of n minus 1. Therefore, the integral of that would be 1 over n plus 1, x to the power of n plus 1. And we justified it a couple of different ways. Number one, if you look at x to the power of n, you are going to multiply that expression by n, and you're going to subtract 1 from its exponent. You get nx to the power of n minus 1. For integration is the reverse process, which means first we are going to use the subtraction and change it to addition, add 1, and then we're going to second use the multiplication, make it division. And that's exactly what we have here. Also, we differentiated the right side to prove this is correct. The derivative of e to the power of x is e to the power of x. So the integral of e to the power of x is e to the power of x. The derivative of ln x is 1 over x. The integral of 1 over x is ln x. The integral of cosine is sine x. The integral of sine is minus cosine x. All of them have a constant, everybody. The derivative of tangent is secant squared. So the integral of secant squared must be tan x. The integral of cosecant squared must be minus cotangent x, and the rest of them, and all of them have a constant. In this case, just as we did with the differentiation, if there is a constant in front of the function, it can come out for differentiation or integration. Same thing for a sum and difference, you do them term by term. That's the concept here. The derivative of e to the power of kx was k e to the power of kx. We multiplied by k. The integral, we divide by k. So we're going to move on from here. So the first few pages, class, you have every piece of information given to you in posted PowerPoint. You don't have to write anything, just pay attention to the concept. In the old days, the concept of method of exhaustion was used to find the area of a shape that we didn't know the area. For example, we know the area of a circle is pi r squared, but they didn't know that a polygon was inscribed. 3 sides, 4 sides, 5 sides, and we would add. As you can see, as we add to the number of sides, the area of the polygon gets closer and closer to the area of the circle. And that's how they did that. Now, if you want to find the area of a surface given, we don't have a geometric shape. We don't have a geometric formula. So we want to find the area of the region S that lies under the curve y equals f of x from A to B. This means that S is bounded by the graph of a continuous function f, which is positive, and the vertical line x equals a, and the vertical line x equals b. So the synopsis of what you see here, everything that is written here is here, class. S represents all the points x comma y such that x is between a and b, and y is between the x-axis, which has y equal to 0 as the equation, and f of x. See, everything is truly explained here, and that thing is pretty interesting. So how do we find the area? Well, we cut it into so many pieces. In this case, I've done just 4 for the sake of argument. And we cut them such that they have the same width, because it makes it easier when it has the same width. We call that width delta x. And delta x is b minus a over n. N is the number of subintervals. For what I've done here would be b minus a divided by 4. So they have the same width. Same width. What is the height? Well, it's not a rectangle, but we assume it's a rectangular shape. We use the left endpoints, right endpoints, midpoints, you name it, as a place where we can find the height. For example, if I use the left endpoints for the first point would be this one. Let's elaborate on that. So this is what's called a Riemann sum. A summation of f of x sub I delta x, as I goes from 1 to n, is f of x sub 1 delta x, plus all the way to f of x sub n delta x, where delta x is defined as b minus a over n. And the function f of x is a positive value, okay, in the interval of a to b. For example, if f of x is x squared plus 1, we want to find the area from 0 to 2, so we are going to approximate that. Number one, here's the graph. It's a portion of the graph class. If we had, here's the complete graph, but the reason we have that portion because we want to emphasize what we want to find, the area under the curve from 0 to 2. By the way, 0 is the A and 2 is the B. Let me clean up. So what do? We cut it into so many pieces. Let's start with some number. For example, 4. If I cut it into 4 pieces, delta x is b minus a divided by n. That means 2 minus 0 divided by 4. And it gives us 1/2. The width is 1/2 or 0.5, and it's fixed. Again, we did that on purpose to make it easy. So we can use which height, any height of our choice. For example, if we want to go with the right endpoints, it looks like that because this is the height of the first rectangle. This is the height of the second one, the third one, and so forth. Therefore, what we need for the height for the first one is the y coordinate of is 4 points. So r sub 4. We call it r because it's the right endpoints. We call it r sub 4 because n is 4. So we get this. I want to make sure we understand how we arrive at it. So delta x is fixed at 1/2. So 1/2 times f of either 0.5 or 1/2. This would be this height, this distance class. When we say f of 1/2, it represents this distance. Then f of 1 represents this distance. F of 3/2 represents this distance because 3/2 is the same as 1.5. F of 2 represents this distance. And for example, 1/2. What is f of 1/2? 1/2 squared, 1/4, and 1 is 5/4. 1 squared, and 1 is 2. 3/2 square it, you get 9/4 plus 1 is 13/4. 2 square it, you get 4, and 1 is 5. So that's how we arrive at those numbers. We put it into a calculator, gives us an area. We're going to do the same thing for the left endpoints. If you want to go with the left endpoints, this would be the height for the first one. This would be the height for the second, third, fourth. Okay. So in other words, for the right endpoints, this one, this one, this one, and this one. Those are the heights. For the left endpoints is this one, this one, this one, and this one. And so, with that being the case, L4, YL, left endpoints, Y4, we chose N to be 4. So the same formula now, f of 0, f of 0.5, 1, 1.5, that's what we have. And notice this part is identical to this part, meaning it really makes the calculation easy. All you have to do keep this. When you calculate this one, just calculate half of f of 0 and add to it. You put it into a calculator and it gives you 3.75. So what is the area? None of the two. The area is somewhere in between. As you can see, this is larger than the actual area under the curve, and this is smaller. So we say this overestimates, this underestimates the area. We're going to repeat the same process class. This time we're going to go with n equals 8 because I want to demonstrate what happens when we go with a larger n. So delta x is b minus a, or 2 minus 0 divided by n or 8 gives us 1/4. So the width is getting smaller, everybody. So it looks like this for the right endpoints, or sub 8. So it's going to be 1/4 times f of, we use all of all of these points except the first point, gives us an answer. For the left endpoints, looks like that. We use all of these heights except the last one for the left endpoints. For the right endpoints, except the first one. And so again, notice these two are identical. So if you were to do this by hand, this part is identical to this part, so you would know what is the sum of that. You keep that, and all you have to do, calculate f of 0 and add to it. In any event, we end up with a different number, 4.1875, and therefore, when n equals 8, the area is somewhere between the two. Number one, if you want to calculate this, one easy way to figure out these points, you just draw a line segment, everybody. And this is A, it happened to be 0 for us. This is B, it happened to be 2. You cut it into pieces. For example, if we go back to those 4 pieces, cut it in half, and again half, and again half. So this would be, okay, all of these are used for the right endpoints. These are used for the right endpoints. So f of this point, this point, this point, this point. And for the left endpoints, those are the ones that are being used. Now, also, I want you to notice that when n was 4, the area was between 3.75 and 5.7. Notice, these two numbers are further apart than these two numbers. And the difference between the two is 2, the difference between the two is 1, which means it's getting better, and approximation gets better as n gets larger. Also, I want you to notice this function was an increasing function from at this point, okay? And it was concave up. So clearly, R sub n overestimates the area. So the area of what you're looking for is actually smaller than that. That's why we say overestimate. On the other hand, because it's increasing and because it's concave up, L sub n would underestimate the area. So the synopsis of what we just said. Suppose a continuous function f is defined on the interval of a to b if the interval is divided into n subintervals so that delta x is b minus a over n. X of 0 represents a, x of 1 is a plus delta x, all the way to the end, b is a plus n delta x, or x sub. A Riemann sum associated with f is the summation of f of x of I delta x, I going from 1 to n. I hope you remember this notation from algebra, which means f of x of 1 times delta x all the way to f of x of n times delta x. And this x sub I can be any point in the interval of a sub I minus 1 to a sub I. In other words, any subinterval, you can use the left endpoint, the right endpoint, the midpoint, or anywhere in between, makes no difference. None of them gives you the answer. Each one gives you an approximation. That's the idea. So in short, what is the geometry and a procedure that is called Riemann sum. Partition the interval of A to B into, let's say, 4 subintervals. Sum, okay? If it's 4, make up 4 rectangles. Delta x, which is b minus a over n, becomes b minus a over 4. And the heights are f of x sub 1, f of x sub 2, f of x sub 3, and f of x sub 4. We are using really the right endpoints. Then you make more, for example, 8 or more rectangles. As the number of rectangles increase, the approximation gets better. So here's the formula for the left endpoints, right endpoints, and the midpoints. And as I mentioned, I wouldn't even bother to memorize that. All I know is that I make up a line segment. Okay. From A to B. I cut it into so many pieces. For the left endpoints, I use all those points. I evaluate the function at all those points, not at B, not at B. For the right endpoints, evaluate all of them except not at A. That would be the right endpoints. For the midpoint, you have to locate the midpoint. So if, for example, let's say these are the endpoints, the midpoint would be somewhere in between. This would be the midpoint. I'm going to evaluate the function at those points. And so the area is approximated, and pay attention to the fact that it's an approximation of summation of I going from 1 to 4, for example, f of x by delta x. So if we did with 4, this is what we get. Okay, that's what it's mentioning. But the actual area, the exact area is the limit of the summation of f of x by delta x as I goes from 1 to n, where delta x is b minus a over n and x of I is a plus I delta x. You have to take a limit. That's why this is the association with the limit when it comes to the integration. Now, what I want to do, this is the FTC, and we are going to discuss that further in short. The first one says the derivative of the integral is the function itself. And the second one says if you want to evaluate this from A to B, you find any antiderivative and evaluate it at the endpoint. So I'm going to discuss that later. What I want to do, I want to explain what this is, what it means. First of all, the terminology is the definite integral, where the definite integral represents a number. This is the integration symbol. This is the symbol was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. Lower limit of integration. Upper limit of integration. Integrand, what we are integrating. Dx, variable of integration, also known as dummy variable. Why is that dummy? It is called a dummy variable because the answer doesn't depend on the variable chosen. The dx simply indicates that the independent variable is x. So if I change this to anything, for example, t, and I make this dt, I get the same answer because this is just a number class. So the integral of a to b f of x dx is a number. It does not depend on x. We could use any letter in place of x without changing the value of the integral. So for example, the integral of a to b f of t dt or the integral of a to b f of x dx, they are identical. Okay, they are identical. Finally, on this page, or its approximation, the approximation of this is the integral of a to b f of x dx is almost the summation of f of x by delta x as I goes from 1 to n. This is called a Riemann sum. The precise value would be when we take a limit of this. The limit of the summation of f of x by delta x as n goes to infinity. This represents an area under the curve if f of x is a positive function. Otherwise, it's the difference of areas. To get us started, we are going to start with the easiest example. We want to evaluate the definite integral of dx from a to b. First, I want you to see what is the function. Therefore, I'm going to create 1 times that, meaning the function that we have if f of x or y is 1, which is a horizontal line. So we want to graph this over a to b. So this is y equals 1. And let's assume a is here, b is here. So what do you want? The area of a rectangle. You have a formula for that. You can say the width times the height. The width would be b minus a, and the height is 1. This definite integral represents the area of a rectangle with a width of a b minus a and a height of 1. Therefore, their product is the answer. And we are done. This is evaluating as the area. Now, I want to show you as a definite integral using f of b minus f of a, because what if the area fails? What if we don't have a geometric shape? So what is this? Your f of x is 1. Find the antiderivative. So I want to make sure we understand that capital F of x would be x plus c. But we are going to use just x because the c has no bearing since we are going to evaluate it from a to b. And this uses this method. So f of b minus f of a, that means first plug in b minus second plug in a. So let me actually write it in front of it. So let me use a different color also. So first plug in b minus plug in a. And that's exactly the same. The difference is this will always work. This one, if we don't have a shape that we are familiar with, we can't come up with the proper answer. Here's another one that we are going to use the area, but we are going to use the signed area, and I'll tell you why in a moment, to find the definite integral of minus 1 to 2x dx. So first of all, here's your function. Secondly, in the interval of negative 1 to 2. So that's a, that's b, very clear. Now, f of x equals x or y equals x is a line through the origin. We want to go from negative 1 to positive 2. Negative 1 to positive 2. So this is the area. This is the area. Now, it's important to know that this represents the difference of areas, not the area, unless it's a positive function. Because this part is positive, we take it as positive and we calculate it. This is as negative, we take it as negative and calculate it, and the difference will be the answer. That's why we called it evaluating integrals using signed areas, and that is extremely important, okay? So with that being the case, we calculate the area of this one, we calculate the area of this one, the smaller triangle, their difference is the answer. So of course, A is 1/2 base times the height. This point has coordinates 2, 2. That means this is 2, this is 2. So 1/2 of 2 times 2 is the area of the green part. This has coordinates -1, -1, which means this distance is 1. We are looking at distance. So the area for the red one is half of 1 times 1, which is 1/2. The difference, that means 2 minus 1/2, is the answer, which becomes 3/2. So what we did, we used difference of areas, signed areas, difference of areas. Area above the x-axis is considered positive, below the x-axis considered negative. Now, if they said, find the area, in other words, when they say evaluate this, you have to go this route. If they say find the area, purely area, then you have to put this in an absolute value and then you can add them up, okay? Now, let me show you again with this methodology that was called FTC, Fundamental Theorem of Calculus. So here's your function, everybody. Capital F of x is what? Half of x squared plus a constant. The reason we're not going to use the constant because we are evaluating this at the endpoints, and if even you use the constant, they cancel each other. So what we have is half of 2 squared minus -1 squared, and I hope you see 2 squared is 4, -1 squared is 1. Subtract that, you get 3, and the answer is 3/2. So you do get the same answer, everybody. Always. Again, what's the difference? This will always work. This may be a shape that we don't know the formula for as to how to find the area. What I'd like you to do, I want you to graph and use sign areas to show this at home. The integral of -4 to 1/6x dx is -45. So do exactly like I did. Graph this function and evaluate it just like that. This is a wonderful practice for you. Please do that. And I'm giving you the answer. Okay. All right. Let's look at some examples. We are going to remember the integration formulas, and we are going to use fundamental theorem of calculus. So the very first thing is look at this function. The antiderivative is 1/8 x to the power of 8. We don't need a constant, and we evaluate it from 0 to 1, everybody. So now we are going to plug in the upper limit first minus the lower limit second. As you can see, 1 to the power of 8 is 1, 0 to the power of 8 is 0, so the answer is 1/8. And here's the tip. Even if we use another antiderivative, meaning capital F of x plus c in the evaluation. So in other words, if I put a plus c here, okay, the result will be the same because capital F of b plus c minus capital F of a plus c, the c's cancel out, right? Plus c and minus c, so you get F of b minus F of a. That's why you want to stick with what you have, everybody. So the result will not change. Let's look at this one. In order to come up with that, so I hope you remember that x to the power of -1 or 1/x are the same. So this is the same as 1/x, everybody. So the answer is ln x, and I'm going to put it in it absolute value. This means, and I'm not going to write the constant because it is a number, the result. Ln of 2 minus ln of 1. As you know, ln of 1 is 0. The answer is ln 2, and ln 2 is an exact answer. Keep the exact answer, everybody. Keep the exact answer. Now, if I didn't put an absolute value, would it make any difference? Because both 1 and 2 are positive. However, I'm going to use the same question, but different limits. And of course, if you don't use the absolute value, the result will be wrong. Why is that? Because you would write, for example, ln of negative 1, which doesn't exist, or ln of negative 2, which doesn't exist. However, in this case, this is ln of 1. In this case, is ln of 2. So ln 1, which is 0, minus ln 2 gives you precisely minus ln 2. Okay? And that is extremely important to understand, everybody, why we are using the absolute value. The integral of 0 to pi sine x dx. As you recall, the derivative of sine is positive cosine, but the integral of that is negative cosine. We don't need the constant. We're going to evaluate it from 0 to pi. So to make life easy, I'm going to keep the negative out, so cosine of x. So minus cosine of pi minus cosine of 0. That's what we do. Now, cosine of pi, again, those are elementary. You should know that from trigonometry. Cosine of pi is negative 1 minus cosine of 0 is positive 1. So the result of the brackets would be negative 2. The negative in front of it makes it positive 2. We want to integrate this from 0 to 2, which means the answer is a number, and we don't need the constant. So this is 5/3 x cubed minus 4/2 x squared plus 2x, and I'm not going to write the constant. We are going to evaluate it from 0 to 2. By now, I hope everybody is comfortable with the power rule. This is minus 4 divided by 1 plus 1, x to the power of 1 plus 1. Okay? All right, so plug in 2 and plug in 0. I hope everybody can see that when I plug in 0, I get 0. So just plug in 2. 0 simply makes it 0 because everything involves x. And this is 8. And actually, this is 4. So this is minus 4. And as you know, 4, because I want to go with the same denominator, 3 is 12 over 3. So 40 thirds minus 4 is the same as 40 thirds minus 12 thirds makes it 28 thirds. Okay. We want to evaluate this integral. And as we did with the differentiation, first we use the algebraic technique to write this one as 4v cubed minus this one as minus 3. So first we do algebraic techniques. So it makes it easy to integrate. So we get v to the power of 4 minus 3v. We don't need the constant. We're going to evaluate it from 1 to 2. So first plug in 2 minus second plug in 1. So v to the, so 2 to the power of 4 minus 3 times 2 minus 1 to the power of 4 minus 3 times 1. So what you have here, this is 16 minus 6, which makes it 10. This is 1 minus 3, which makes it negative 2. And 10 minus negative 2 makes it 12. Because it's 10 plus 2. Again, we make up 3 fractions, everybody. Divide this one by this one gives you 1. This one gives you minus 7 over x. This one gives you 2 over x squared. So 3 fractions. By the way, we have done this already, okay? But we haven't evaluated like this. So we did do it as a antiderivative, but not as a definite integral. And so we are going to rewrite minus 7 over x as minus 7 times 1 over x, and the other one as 2x to the power minus 2. So it becomes clear that this is obviously x. This is obviously minus 7 ln x. I hope you remember that. This one, again, I remind you how we did this. This one, we said 2 divided by negative 2 plus 1, x to the power of negative 2 plus 1, which makes it negative 2x to the power minus 1, or negative 2 over x. And we're going to evaluate from the lower limit 1 to upper limit 3. First, we are going to plug in number 3 minus, second, we're going to plug in number 1. So plug in number 3 and plug in number 1. And we're going to evaluate this. So what happens here, class, believe it or not, there was only, I want to make sure everybody understands, there was only one step of calculus. This was algebra, calculus, algebra, algebra. We're going to finish it with algebra or basic math. So first and foremost, ln1 is 0. So 1 minus 2 makes it negative 1. With this negative 1 makes it positive 1. I didn't touch the first part. So I kept the first part intact. Okay, everybody? But the second part changes to a positive 1. So what happens now? 3 and 1 is a 4 minus 2/3. 4 is 12/3 minus 2/3 is 10/3. I don't touch minus 7 ln 3 because this is an exact answer, everybody. Okay, this is an exact answer. In calculus, normally we want an exact answer. Okay, so not a lot of calculus steps. We have already done this. I hope you remember that. It was t plus sine t, okay, and a constant, but we're not going to write the constant. 1, remember the independent variable is t, so 1 gives you t, not x. Cosine of t, the derivative is negative, but the integral is positive sine t. We have already done that, but we haven't evaluated. So let's plug in pi over 2 minus, let's plug in 0. Plug in. This is 0 because sine of 0 is 0. So you have pi over 2 plus sine of pi over 2, which is 1. And we keep it as that because this is an exact answer. Please understand pi is not 3.14, okay? But rather, it's an irrational number. 3.14159, and it continues indefinitely. We want to integrate this, and we are going to change this to x to the power of 1/2. And this is x to the power of 1. So we have 5x to the power of 3/2 plus 3x to the power of 1/2. Algebraic step so far. We are going to use the power rule. So 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1, plus 3 divided by 1/2 plus 1, x to the power of 1/2 plus 1. Evaluated from 1 to 4. We don't have a constant because this is a number. Again, 5 divided by the exponent plus 1 plus 3 divided by the exponent plus 1. Okay? Now, this is 5/2. And I hope you see 5 divided by 5/2 is 2. This is 3/2. Same thing, 3 divided by 3/2 is 2. Again, please understand this was the only, I put the asterisk next to it, I put the asterisk next to it, the only calculus step. Everything else is algebra. We are going to plug in 4, and then we are going to plug in 1. Basic math, we want to evaluate it. So 4 to the power of 5/2 means the square root of 4 to the power of 5. And 4 to the power of 3/2 means square root of 4 cubed. Now this is 2, and 2 to the power of 5 is 32. And 2 times that is 64. So this is 2 cubed, it's 8, and 2 times that is 16. 1 to any power is 1. To the power of 5/2 to the power of 3/2 makes no difference. So this is 2, and 2 is 4. So minus 4. 64 plus 16 minus 4 is 76. So a lot of algebraic steps, if you will, or basic math. So that's fundamental theorem of calculus that is being used here, everybody. Let's look at an application. Can somebody read this for us, please? Anyone? I'm sure I'm getting tired of my voice. I'm sure you're getting tired of it too. So somebody read that, please. Anyone? Okay. Water flows from the bottom of a storage tank at a rate of R of t equals 200 minus 40 liters per minute. Find the amount of water that flows from the tank during the first 10 minutes. So we're going to look at the concept known as a net change or accumulated change theorem. If capital R of t represents the amount of water that flows from the tank at time t, then the rate of flow is given by capital R prime of t or lowercase r of t or 200 minus 4t. The amount of water that flows from the tank during the first 10 minutes will follow the following theorem. The integral of a to b f of x dx is capital F of b minus f of a is also known as accumulated change or net change. Therefore, take the integral of this times dt from a to b from 0 to 10. Again, I wanted to go over this theorem for you. And so this gives us 200t. This gives us minus 2t squared. We're not going to write a constant because we are evaluating it from 0 to 10 because it's going to give us a number. So 200 times 10 minus 2 times 10 squared. If you plug in 0, you get 0. So this is 2000, right? Minus 2 times 100 minus 200, it's 1800 liters. Please pay attention to the units here. Is liters per minute at the rate. So the function itself as units of liters. Anybody you want to read this for us, class? Okay, let's do it. Many fish grow in a way that is described by the von Bertalanffy growth equation. For a fish that starts life with a length of 1 centimeter and has a maximum length of 30 centimeters, this equation predicts that the growth rate is 29 e to the power minus x centimeters per year, where x is the age of the fish. How long will the fish be? After 4 years, and they're asking for 1 decimal, everybody. They're asking for only 1 decimal place. Let capital L of x represent the length of fish at age x. Then the growth rate, which is L prime of x, or dl dx, is this one. And this piece indicates L of 0 is 1. Therefore, the amount of increase in the first 4 years would be the integral of this piece, of course, with dx from 0 to 4. This is the amount of increase. As you recall, in the case of exponential, we're going to divide by -1. It so happened division or multiplication by -1 makes no difference, gives us negative 29 e to the power minus x. We don't need the constant because we are evaluating from 0 to 4. So let us plug in 4 and 0. So we're going to keep the negative 29 out. It makes life easier. And then e to the power of minus 4 and then minus e to the power of 0. That's what we get. This is 1. E to the power minus 4 minus 1. You put in the calculator and you end up with 28.4688. There are many, many decimals. This is the amount of increase, but L of 0 was 1, that the initial size, add them up. And then because they said 1 decimal, so first you put a lot of this. Don't do the rounding in the middle of your steps, but rather the last moment, because otherwise the number will be off. So about 29.5 centimeters. This is one way to do that. So what I want to show you is actually the second method. The second method is to take the integral of this function. And since we did the definite integral, we know the answer is this one plus a constant, and we know L of 0 is 1. Remember, this, okay, the order was not right. Let me just, so this gives you, comes out at the end. This will give you negative 29 equals e to the power minus x plus a constant, where L of 0, we know it to be 1, and that's a general solution. Now that we have this pair, 0, comma 1, we can find the constant and it becomes a particular solution. So let's plug in. As you know, this is 1. So we have minus 29 plus equals 1. C becomes 30. This is the formula. And now if you plug in 4, that order was wrong. If you plug in 4, everybody, you come up with the proper answer. If you plug in 4, you come up with the proper answer. As you can see, this one is the same as this one. And of course, you do the rounding accordingly.